So we're on section 1.2 and we're going to be talking about measurements in chemistry. So measurements in chemistry. Well, measuring has to do with mathematics. And mathematics, we know, is the language of science. I like that because science has to work in some language, while mathematics shows us. And so mathematics and science go together. It's integral in all science. We have some form of math. I like this, what's down here where the famous British scientist, Sir William Thomson, Lord Kelvin. You know, so he was named Lord Kelvin, but his real name was William Thomson, and he lived in 1824 to 1907. When you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, it may be the beginning of knowledge, but you have scarcely in your thoughts the advanced stages of that science. Basically saying, you know, if you don't have math, you just have it in your head. You need to have the language of science so you can present your science to other people. So that's what math is. It says, in fact, modern science did not exist until man could accurately measure such quantities as distance, time, mass, volume, temperature, and pressure. See the picture there of measuring, how important it is to measure in science. Let's go on to the next section. Precision and accuracy. So precision and accuracy are not the same. And for the first part, precision has to do with consistency or reproducibility, being used different measurements by different people. You know, some precision means that some measurers are uncertain, you know, and different people measure differently. So that's precision. But it says right there, precision has to do with the consistency or reproducibility of measurement and is closely related to the measurement's uncertainty. For example, two people may read an experiment differently, leading to slightly different values, or the same person may get several slightly different values. Such errors in measurement are called random errors, so random errors, because they tend to fluctuate randomly about the true value. Random errors reduce the precision that is possible. So when you think of random errors, you're going to think of precision. So what is accuracy then? Well, let's look at the definition for accuracy. Accuracy has to do with how close measurement is to the actual exact value. So when you know the exact value and you know that someone has missed the mark, they're not very accurate, are you? So accuracy is just how close it measures to the actual value. It's not different measurements like precision is. So systematic errors may be because of the accuracy, cause the accuracy, like a defective instrument that you're using, a miscalculated instrument. It's a poorly designed instrument that miscalculating things. These affect the systemic errors and affect accuracy. So if you have a measurement, if you have a scale, say your scale's off. So those are systemic errors, as those make it inaccurate because of how the measurement is not measured up, is inaccurate, or the scale is inaccurate, or inaccurate values. So uncertainty. Uncertainty is the third thing we're going to talk about. And uncertainty are numbers obtained. There's certain numbers. Okay, numbers obtained by counting are always certain. If you go 1, 2, 3, 4, 5, those numbers are certain. You know those numbers. If there are 21 students in your class, you don't have to wonder if the true number is 20.6 or 21.5. The number must be exactly 21. Likewise, if you define certain values are certain. So like if you have 100 centimeters in 1 meter, there are exactly 100 centimeters in 1 meter. If you have 2.54 centimeters in 1 inch, there are exactly 2.54 centimeters in 1 inch. Because they have no uncertainty, values obtained by counting or set are called exact numbers. So you're going to remember the question. There's two ways to get exact numbers. One is by counting and the other are by defined values. Those two things. I think that's a test question. So uncertainty, uncertainty or any other areas could be uncertainty, but not exact numbers by counting or by defined values. Okay, let's go on to basics. Says measurements in the real world cannot be perfectly precise or accurate. There's always some uncertainty in a measurement unless they're exact numbers, right? Or defined values. So here's a picture down here. See, you see the difference? See, this is poor accuracy. You shoot and you didn't hit the bullseye. And this is good accuracy. You shot and you hit the bullseye. Now precision is you have different people shooting. See all the different red dots for people shooting? See the precision? They're all shooting. And the precision is kind of off because all of them are not getting into the bullseye. And then you have the other good precision. They're all getting into the bullseye. Just remember precision has different, you know, the precision has measuring different values, right? And the good accuracy is missing the mark, or bad accuracy is missing the mark. Okay, now let's go on to the metric system. What the metric system is. Now you've been studying the metric system, so you should know a lot about this. So we needed a uniform system. Well, the system of a system of measurement is a collection of compatible related units that can be used to measure. So everybody has the same system of measurement, no matter which country you're in. It's going to be worldwide. Scientists want to look at measurement the same. So in doing this, the system of measurement most commonly used in the United States is the foot-pound system, okay? We're going to find later on that the world doesn't really want to use this foot-pound system, but we use it in America. So it means basically we go by feet, we go by pounds, and we go by seconds, right? Although sometimes called the English system, it actually dates back to Rome, Roman times. Such units as the inch, the foot, the mile, the ounce, and pound, they came directly from Rome. And other units came in the Middle Ages, such as the yard and the acre. Although the foot-pound system is common in the United States, it is poorly suited for the types of measurements and calculations used in science. So now we've decided, instead of going from the foot-pound system, we should go to the metric system, because this is a worldwide standard for systems of measurement. So now we'll have a worldwide. So if scientists in the United States want to compare to their studies to other scientists, they're all going to use the same system, this metric system. It was developed in early 1790 by the French National Academy of Science and is based on a few basic units that can be defined very accurately. So it was defined by the French in the 1790s. Units that are smaller or larger than base units are related to each other by powers of 10. So just remember, the metric system goes by powers of 10. Thus, the metric system is called a decimal system. Deci means 10. So it's decimal system, metric system. The metric units most common encountered in everyday measurement are kilogram. Kilogram uses mass. That's how you weigh something in kilograms. The meter is a unit of length. The liter is a unit of volume. Since the late 1800s, the units of the foot-pound system have been defined now in terms of metric system. So we're going by the metric system now. So this is, you should know about the metric system. I'm sure you've measured in the metric system before. So let's look at the table here. Kind of important on the prefixes of the metric system. Mass, okay, we went into, first of all, let's look at, we want to look at how we measure length or volume. And of course, we measure length and volume in what? We measure length and volume. The SI is the meter. And a meter is the distance that light travels, which is 1/299,792,400,000. It's quite a bit. Let's just say that. Or 299,792,458 seconds. That's quite a bit. I said billion, but it was million. So let's go on to talk about that. The measuring, here it is right here in this number. Measuring length and volume. The standard SI unit of length is the meter. 1 meter is defined as the distance light travels. You see how fast? 1/299,792,000,000, or 299,792,458 seconds. Okay, a centimeter is 1/100th of a meter, is about 2 inches, or roughly the width of a sugar cube. The milliliter is about the width of a large paper clip, 1/1000. Milli means you divide it by 1,000, a centimeter by 100, and down to the kilometer, which is just under 1,100, I should say, yards, or about 6/10 of a mile, is a kilometer. So kilometers is smaller than a mile. So, so these are the measurements. You see how 1 centimeter, here's a ruler here, and you see the 1 centimeter length and the difference between the inches there. You'll see that in almost every ruler. So let's go back to our table. Okay, so these you can see the prefixes. It's important about these prefixes, right? So you have the prefix atto, 1 quintillionth. You have femto, 1 quadrillionth. Pico, 1 trillionth. Nano. So we usually don't go up to those atto, femto, and pico, but now we have nano, which is 1 billionth. The micro, see the micro sign is 1 millionth, 10 to the -6th. And the micro, our milli, is 1,000th, 10 to the -3. Centi is 100th, 10 to the -2. Deci is 1/10, 10 to the -1. Deca is 10 times, would be 10 to the 1. Hecto, 100 times, 10 to the 2. Kilo, 1,000 times, 10 to the 3. Mega, 1 million times, 10 to the 6. Giga, 1 billion, 10 to the 9th. Tera, 1 trillion. So these things are important to know. So when you have a prefix, you know it's either going to be 1 billionth or 1 billion, depending on whether you're getting larger or getting smaller, if you're talking about that. But you need to know these prefixes. If you don't know them, you could look them up, but usually the common ones you need to know are deca, centi, milli, micro, nano. The ones that are highlighted, kilo, mega, those are the common ones when you come to prefixes. Okay, so let's go on to the next page. So now we're going to talk about, so we were talking about mass, and we're talking about length, about length, and now we're talking about one very important measure derived from length is volume. So the most familiar metric unit of volume is liter. You see a liter? You got a liter of Coke, let's say, and it's defined at 1,000 cubic centimeters, right here, 1,000 cubic centimeters, or approximately the volume of a cube 4 inches on each side. A liter is just larger than the U.S. quart. So that's going to be a test question. Which is going to be larger, a liter? That's always a test question, a liter or a quart. So you know a liter is slightly larger than a quart, right? Which one is bigger? A liter. So if you're going to get a quart of something and you got a quart and a liter and you want the most, you're going to get a liter because it's slightly larger than a quart. Measurements of quantities smaller than 1 liter are always in milliliters. So milliliters are 1,000th of a liter. A milliliter is the same as a cubic centimeter and is roughly the volume of a sugar cube. So milliliters and cubic centimeters are the same thing. Just remember that. And there are about 5 milliliters in a teaspoon. So if you have to take some cough syrup and it says take a teaspoon, it may say take 5 milliliters. It's because basically the standard unit, it should be in milliliters, although you can take a teaspoon and get the same measurement. Okay, the measurements of mass. I'll say. So mass and weight. Let's look at this picture up here. This picture of mass and weight. So what do you think about mass and weight? Mass versus weight. Mass is the quantity of matter in the object. It's always the same. So whereas weight is the force of gravity upon the object. So weight can differ. So weight can be very light on the moon. You know, that huge 75 pound or, you know, thing that or maybe 75 ton thing can be very light on the moon. So gravity and weight weight changes upon the gravity on where the gravity on Earth you are, or whether you're in space. But mass, so when you weigh yourself, what are you taking? Well, when you weigh yourself on the scale, it's always going to be gravity, right? But mass is the quantity of matter, how much matter is in the object. So that's the difference between gravity and mass. Okay, let's go on here. We're going to talk about density too, but let's continue to talk a little bit about, mass too. So, let's see what I wrote down here. So, a gram is the mass of 1 milliliter of water at a maximum density. So when you're talking about grams, let's go up the top here. We're talking about grams. When you're talking about grams, that's what you're going to be talking about. The gram was originally defined as the mass of 1 milliliter of water at its maximum density. Because the gram is a small unit, kilogram is more commonly used. So kilograms are 1,000 grams. So because gram is a very tiny unit, kilogram, like when you're measuring, say you get on an airplane, they want to measure in kilograms, right? A kilogram corresponds to the mass of 1 liter of water at its maximum density. So 1 liter of water at its maximum density is a kilogram. So that's pretty important there to know. Now let's talk about another factor, which is density. So what is density? Density is usually represented by the lowercase p. When you see this p sign, that means density. And it measures how things are compact, the compactness of matter. Mathematically, density is the ratio of a substance mass to its volume. So you'll see this equation and you just fill in the blanks when you're doing this equation, right? So if you need to know, the density is the P, mass, so you take, the mass or the weight of the object divided by its volume, and you'll get the density. So you'll probably have to do some of those. And it's most commonly measured in grams per cubic centimeters or grams per milliliters. Remember, a cubic centiliter and a milliliter is the same thing. So let's go at the top here. Okay, talking about density. Density is most commonly expressed in grams per cubic centiliter or grams per milliliter. Unlike mass or volume alone, density provides information about the identity of the substance. So osmium is the densest occurring element, having a density of 22.5 grams per cubic centimeters. And mercury has a density of 13.6 grams per cubic centimeters. And balsa wood has an approximate density of 0.2. See how dense this object, this osmium, is compared to mercury and on to wood. So you can see how dense. Water's density is always just 1. 1 gram per cubic centimeter at room temperature is water's density. So everything kind of goes by water's density. So let's look at this table down here. It kind of tells about denses. So you have 1 kilogram of air is all this air. 1 kilogram of cork is quite a bit. A pine is a little bit littler. And then water, that's 1 kilogram of water there. And 1 kilogram of glass is denser. And then onto marble and aluminum and iron and lead and gold. So 1 kilogram of gold is pretty dense, pretty heavy comparatively, see? So that's how density basically says mass divided by volume is the density. So let's go back up here. It's another thing we need to know. Measuring temperature. So in chemistry, temperature is most commonly measured in degrees Celsius, the Celsius scale, right? And it assigns the value. 0 degrees Celsius is the freezing point, and 100 degrees is the boiling point. Room temperature of Celsius is about 20 to 25 degrees Celsius. And if you're taking your body temperature, it's usually around 37 degrees Celsius. So, but this also can be expressed on the Fahrenheit scale, right? So we use the Fahrenheit scale more than the Celsius. So when does water boil on the Fahrenheit scale at 32 degrees, it freezes at 32 degrees and it boils at 212 degrees. That's in the Fahrenheit scale. And there are, basically when you take these two scales, you have to convert them. You know, I could say they were 100 over 180 is 5/9. So basically to convert these, you use these formulas here. So it's important that you kind of know these formulas. Temperature of Celsius and temperature of Fahrenheit. So temperature of Celsius equals 5/9. You take the temperature of the Fahrenheit and you subtract 32, and then you times it by 5/9. And then if you want to find the Fahrenheit, you take the temperature of Celsius and you times it by 9/5, and you add 32 degrees. So you just know that when you get the number, it's going to look like the Fahrenheit has a bigger number than the Celsius number. But that's how to convert it. And so we need to know those conversions. Those will probably be on your questions, how to convert from Celsius. So taking those scales, 32 degrees, and you take the freezing point. Or let's look down here. I think there's a picture of here down here, the bottom here, if I can find it right there. These are the scales here. So we have the Fahrenheit scale, we have the Celsius scale, and then we have another scale called the Kelvin scale. It's important that we know the Kelvin scale because that's the absolute 0. So the coldest possible scale. So at absolute 0 would be the coldest possible, would be the Kelvin. Kelvin never goes by temperature or in degrees, you know. So here's Kelvin at the coldest possible is absolute 0 is 0 Kelvin. At absolute 0, as you can see, the Fahrenheit is negative 459.67 degrees. The centigrade is negative 273.15 degrees. And you can see that. That's the boiling point of nitrogen. You can see the different ones, the boiling point of nitrogen. Now let's go up to the freezing point of carbon dioxide. You can see the numbers. Now you can go up to the scales and you see where negative, it's kind of weird here. It's, Celsius and Fahrenheit are the same here. And it's at 233.15 degrees Kelvin. And you see those two. And then you go up to the freezing point of water is at 273.15 Kelvin right there. And then you go on to 0 degrees at Celsius and 32 degrees. That's freezing point. Then your normal body temperature is 310.15 Kelvin, 37 degrees Celsius, and 98.6 is our body temperature. And then on to the boiling point of water, 373.15 Kelvins, 100 degrees is the boiling point on Celsius square, and 212 is the boiling point of water on the Fahrenheit scale. So those things, just remember there's 3 different scales, and it's important how temperature goes. The reason they go by the Kelvin scales is some scientific equations require absolute value. That means they are so cold and you can't measure them very well by Celsius or Fahrenheit. So that's why the Kelvin scale was developed. Okay, so how do you change this? You're going to have some equations on how to change this. Well, here's your formula you need to know. So temperature Celsius equals temperature Kelvin minus 273.15. So basically, if you want to know, the Celsius of a Kelvin number, you take the Kelvin number and you subtract 273.15, and then you'll get the Celsius number. Now, what if you want Fahrenheit? If you want Fahrenheit, you have to turn the Fahrenheit to Celsius before you can use this equation. So first of all, you turn the Fahrenheit, use the equation over here to turn the Fahrenheit into Celsius, that first equation, and then you go back here and then turn the Kelvin into Celsius. So there's 2 steps, okay? So let's see. Other SI units. How about time? How is time measured? In seconds. Both the foot-pound system and the scientific system, they use seconds. So it defines the second as the required time for an atom of cesium, 133 cesium, to vibrate a particular way, and this many times, 9,192,631,770 times. Scientists estimate that this is the atomic clocks, and they're based on this standard, so they're very accurate to within 1 second every 60 million years. So just think, by these seconds, we go by the atomic clock. There are also other measurements that measure energy, power, and magnetism. And some of these units are the watt, the volt, and the ampere. And they're usually familiar, especially when we're measuring electricity and such. And there are other units too. The joule. The joule is the unit of energy, and the Pascal is the unit of pressure. So just be familiar on what these units measure. So let's look at this chart here. You can see now metric units, the length, a meter is M, mass is a kilogram, and that's kg, volume is a liter, that's L. Just know those symbols. Time is a second by S, temperature, degrees Celsius is a degree Celsius, degree with a C. Absolute temperature is kelvins with a K. Pressure Pascal is PA. Amount of substance is measured by moles. Energies by joules. We got electric current for ampere. Volts, voltage. Powers are watts. Force, Newton. Frequency, like hearing sound waves, are measured by hertz. Luminous intensity is a candela. So some of these, the ones in dark are familiar, and the other ones probably are not familiar to you. So may not be familiar to you. So converting units. Okay, we're going to go on to the next section, or the next video on converting units, because it's going to take a little bit of time.